In this video, I will go over the homework that follows the lecture 20.2 that discusses in which we discuss the logistic growth model, also known as the constraint growth model. And as always, I hope that you watched these two lectures. And let's go ahead and jump right into the homework. So the first question is, we are given some data and we have to write the equation. And before we do that, let's go ahead and take a look at what the equation looks like. I think we have it right over here. And I probably need to copy it over. So the solution to the logistics equation looks like this. This part is pretty much almost the same as the unlimited growth, but then we also have this part. And here we have L is the carrying capacity. So that's the largest the population can be. P0 is the initial population. And R is the growth rate. So this is what we know. Now, looking at this problem, what do we have? We have R to be given as 0.43. The carrying capacity is L given at 4,270,500, and the initial population is this. Now, this is the solution. However, this particular exercise is asking us to write the equation, and the equation, you can remember it or you don't have to, but the idea is that the rate of change is must be equal to 0 when initial population is 0. Well, I guess when the population is 0, but it also must be 0 when you are at the carrying capacity. So but outside of that, it has to be proportional to this number. And let me just double check that I'm not butchering it, and I am kind of butchering it. If you also take L out, then so yeah, like this needs to be divided by L. So when you divide this by L, you get we get the logistic equation. So for our problem, we just really need to plug that in. So the answer to our question is this. R is 0.43, P is the function, L is the carrying capacity. And I don't know if they want us to write the initial value here or not, but let's just write the equation first. And if they don't like it, we'll put a comma and we'll add the initial value. Oh, they did like it, but I was ready to also throw the initial value right in there. Now, before we move on, let me copy this function into Desmos in case if I ever need it. And for example, here we had the following information provided to us. and it's fair to say that t is greater than or equal to 0 here, and r is equal to 0.43. So let's just have it here, just in case, and let's move on to the next question. So in this case, we are given the equation and it says for the function below with an initial value less than the capacity, would the function be increasing or decreasing? The idea is simple. If you are not at the carrying capacity, you will be approaching that carrying capacity, but it depends on your initial value. If your initial value is below carrying capacity, you will be approaching it from below. If your initial value above carrying capacity, then you will be approaching the carrying capacity from above. In this case, initial value is less than capacity, so the function will be naturally increasing. That's why it's called the population growth. However, if you have too much of something, then population will be naturally decaying, but this is not what the problem was asking us. So here, identify the growth rate for the logistics equation. And again, here we just have to recognize that this is the logistic equation, and the growth rate is this number over here. This is your growth rate. So that's all it's asking us. Now, in this question, we're given everything. And what is the differential equation? So we just need to write the equation. So the equation will be this. So let's just copy it over here. And we finished the first objective, so let's go to the next one. In this, we are given the equation, but again, the good news is that we only had to solve this equation once. So that's what we learned in a calculus class, how to solve it. Once we solved it, we can use that knowledge forever. It's just like you only had to learn how to derive quadratic formula once. After that, you get to use it. Here's the same thing. We know how to solve it. We solved it. Let's just write the answer. The answer is going to be this. I saved it earlier, right here, right? So the answer will be LP0 to the RT divided by L minus P0. So as long as you know what your L and P0 and R are, then you're good to go. So this is our R, this is our L, and this is our P0. So the solution will be L times P0 times E times 2.51 t divided by L minus P0 plus P0 e to the power RT. And the rest is just typing. I think I copied everything. And we're good. Now, why doesn't it look like this? And to be honest, the answer is the truth is that this is not the simplest way to write this formula. We can always simplify it further by dividing everything, the numerator and the denominator, by P0 e to the RT. So we would have L at the top. We would have plus 1 over here. And here we would just have L over P0 minus 1 times e to the power negative RT. And technically this is an easier way to write the formula because it requires less typing. So next time we have to do this type of question, we'll answer it this way. And there you go. So in this problem, L is 9120500, P0 is 2,280,125, and R is 0.84. So I'm just going to type it the way I'm showing it over here. So we have L in the numerator. In the denominator again we have L divided by P minus 1 e to the negative RT plus 1. 9120500. Here we can put 1 plus e to the power negative. Oh, forgot about R. R is 0.84. And here we write 9120500 over 2280125 minus 1. Of course, we can compute that number, but that's not the point. Interesting. For some reason, it doesn't like it this way. Does it mean if I write it the old way, will it accept it? I don't know, let's find out. So the old way is we're going to write L times P0 times e to the power this divided by let's see. So we have I wonder why I didn't like it. Interesting. Anyway, let's continue. In this case, we are given the equation. Once again, don't need to solve it. We already solved it once. You just need to be able to identify the key parameters such as R, such as L, such as P0. Then you should be able to write the solution, or you can use Desmos here. So and now make sure you answer the question. So the question here was find P of 8. Finding P of 8 is as simple as plugging in 8 into this formula and computing it. And now we just have to read the rounding instructions. And we have to round to the nearest whole number. So the answer will be 471,999,8. That's it. Don't overthink it. Same problem, right? So we know R, we know L, we know P0. We plug everything in. Actually, here we don't plug everything in. We have to write the solution. So it's going to be 2,228,500 times 114025 e to the power 2.03t divided by 2,228,500 minus 114025 plus 114025 e to the power 2.03 t. The only thing, I'm not sure why it's marking it wrong, as maybe because it's asking find the general solution. So when we look for general solution, it's one of the prior steps before we actually get to find C. Let me see. Did I? It's right here, right? So this is the general solution. It actually right here, right? So this is my general solution. Right over here. So we have limiting capacity divided by 1 over C. So let's just make that adjustment. But I would consider that like to be a trick question, I guess. Maybe. I don't know. Let me take a snapshot of this. So the general solution will look like this. Because I haven't been reading the previous tasks carefully, so previously I didn't like that one. So it's really tough here. I'm afraid to make a mistake at this point, but let's go with this. If it doesn't like it, it doesn't like it. We're gonna have this. We're gonna have e to the negative. The coefficient will be interesting. Why didn't it accept my first answer? 2228500. That's a mystery to me. Why didn't it accept my answer? But anyway, we have to move on. All right, next problem is going to be number 9. We identify R as 2.16, L as 2720000, P0 is 1360000, and we ask to find P of 2. To do that, we're going to plug everything that we know. So we have here 2720000. P0 is 1360000. R is 2.116, and we need to find P of 2, which is 2684299.3. So we're rounding to the nearest whole number, so it's going to be 2684299. Another one of this. R is 2.83, L is 2650500, P0 is 53010. We're gonna write P of t as L P0 divided by e to the RT. Here we're gonna have L minus P0 plus P0 e to the RT, and I'll just enter it. 2650500 times 53010 times e to the power 2.83 t. If it's not gonna like this, I don't know. Maybe I made a typo earlier. I'm not sure, but let's move on. Another one of these, right? So we have R is 1.78, L is P0 is, so we're going to write the answer as we did many times already today. L P0 e to the RT, L minus P0 plus P0 e to the RT. So here we're going to have 740,500 times 5924123 times e to the power 78t. Getting pretty boring, right? They give us everything here. So P of t here will be LP0 e to the RT divided by L minus P0 plus P0 e to the RT. So with everything being given, we have 5920500, 59205, 2.9t. Here we have this is L minus P0 it's pretty boring. So in the next problem, we are asked, so we have a population function which we can find using the logistic equation, but what we are, so I guess let's find it. So it's going to be LP0 e to the RT divided by L minus P0 plus P0 e to the RT. And let's see, we have, let's try to understand the question. Estimate the number of years it will take to reach the carrying capacity by finding the time to reach 99% of the capacity. So we're basically looking for this. We want to solve this equation. We want to find where the function is equal to 99% of the carrying capacity. That's what we want to do. And to solve that means we take LP0 e to the RT. I guess we don't need to. Let's just plug everything into Desmos. So L is 164400. P0 is this. R is this. And let's put it here. We have L is 164400, P0 is 20550, R is 07, and we're looking to solve P of t to be equal to 0.99 L. I guess I'm not sure if because it doesn't like t. So if I use x instead, then setting this up, it doesn't look at it does anything. So I guess, can we do this by hand? Sure. So all we have to do is we have to take this equation, have to set equal to 0.99 L, which L can be reduced, and now we need to solve this equation for t. So we're going to multiply both sides. Now we're going to subtract this from both sides. So we have 0.01 P0 e to the power RT is equal to 0.99 L minus P0. So we isolate e to the RT. It's going to be 99 L minus P0 divided by P0, and t will be equal to 1 over r ln of, I wonder if it's some sort of formula. So let's just throw it in here. We're gonna have 1 over r ln of 99 L minus P0 divided by P0. So the answer is 93.443. We have to round to the nearest year, so The answer is 93. Interesting. Somehow that 99 doesn't pop up in their solution, but there's clearly some pattern here. So let's continue. We have problem number 14. So in this problem, we are given the rate, the carrying capacity, the initial population, and the question says to find, so we need to solve P of t being equal to this much. We have to solve it for t. So let's do it. We have, actually, I don't know how to do it. So, well, I mean, I don't know how to do it fast without getting our hands dirty. But here's the equation that we're working with. We have we have L P0 e to the RT divided by L minus P0 plus P0 e to the RT. And we want that to be equal to 104,756. So we're going to multiply everything. So let's just give it, let's give this number a name. So let's call it V, some value, right? So we're going to multiply both sides by the denominator. We're going to subtract this from both sides. So we have L minus V P0 e to the RT is equal to V L minus P0. And now we're going to isolate e to the RT. So it's going to be V L minus P0 divided by L minus V P0, like this. Actually, pretty cool looking formula. And now we're going to isolate for t, so it's going to be 1 over r ln of this. So honestly, I would rather just plug it in as a formula. So let's just type this v is equal to 104,756, and we got this formula 1 over r ln of v times L minus P0 divided by P0 times L minus V. It's a pretty good looking formula. And what's the rounding instructions? Nearest year, so the answer is 95. I think I forgot to adjust the numbers in the formula. So R is equal to 0.09, L is equal to 250509, P0 is equal to 83503, and the answer is now a little bit different. Oh my god, why? I said I don't know the way to solve it fast. I do know the way to solve it fast. The graph of P of t is this, right? And we're trying to find when the graph will hit a certain level, which is v. So we just need to graph y equals v, and whatever these two intersect, that's the answer. So the answer is 4.032. I said earlier I don't know how to do it fast. So yeah, totally don't need to use this formula. I can just graph it and see exactly where the answer is. That was very silly of me. So the answer is 4. All right, we have another chance to redeem ourselves. How long will it take to reach a population? So we're trying to solve P of t equals 122,502, and L is equal to 295,659, R is equal to 8%, P0 is equal to 98553, and to solve it, I'll use Desmos, and I'll do it in 2 different ways. One, I'm going to use a graph. So here's my R, here's my L, here's my P0, here's my value. So I can see clearly that the answer is 4.338. So to the nearest year it will be 4. However, we can also use this formula and we'll get exactly the same answer, 4.338. So we're now more than certain that the answer is 4. And we completed this assignment. If you have any questions about logistic equation and how to use it in applications, please reach out.